Hi everybody. This is the second video in a series of 3 about powers in AC voltage circuits. In the first video we looked into power in a resistor and now we are going to look in power in an inductor. Suppose we have this electrical circuit diagram in which we have an AC current source over here which is depicted here, and applied to that circuit we have an inductor. Suppose my sine wave current source has this expression. It's equal to Im, which is the amplitude of the current, times the cosine of omega times t. Could also be a sine, but in this example it's a cosine, which doesn't matter because the cosine is a sine which is shifted by 90 degrees. Well, when that is the case and we want to look to the voltage across the inductor, we can apply this formula which says that the voltage across the inductor is equal to the inductance value times the derivative of the current. So E is L times di dt. Well, let's do that mathematical expression and then we get E is L times the derivative of this function, so L times Im, the amplitude of the current, times the derivative of a cosine, which is minus the sine of omega times t, the minus over here, and then we have to use the chain rule, which says that we have to take the derivative of omega times t, which brings us omega over here. So this is my expression for the voltage. But because we had a cosine definition in the current, it's more or less it's easy to see when we transform this sine in a cosine. So minus sine omega times t is equal to the cosine of omega times t plus the phase shift of 90 degrees, p over 2 radians. So then we get the voltage E is equal to omega times L, which is here, which is the impedance of the inductor, times the amplitude of the current, Im, times the cosine of omega times t plus pi p over 2. And we can replace this by the amplitude of the voltage, Em, so in our definition, Em equals omega times L times Im. So what we see is, again, the voltage also has a cosine wave expression. It's only shifted by 90 degrees, or we can say that the voltage leads the current by 90 degrees, or by pi over 2 radians. We also see that both the current and the voltage have the same frequency. Now let's look to it in a graphical way. So in this picture over here, we have the blue curve, which is the current, and we have the red curve, which is the voltage. And suppose that my t is 0 point is somewhere over here, then we see that the current is a cosine, which is over here, and we see that the voltage is a cosine which leads the current. So it's a cosine and it leads the current by 90 degrees. When we want to calculate the power, instantaneous power, then we have to multiply at every point in time voltage and current. So let's do that, and then we get the green curve over here. So we multiply the red curve by the blue curve at every point, which leads to this green plot over here. And that is my power. And what we see are two things. Well, first of all, the frequency of this power is 2 times the frequency of the voltage and 2 times the frequency of the current. Secondly, we see that the average power is equal to 0. This is my dashed line, which is the average value of the power, which is equal to 0. And that is because we have equal parts which are positive in that sign, as we have equal parts into the negative part of the sign. So my average power is 0. Well, can we calculate that in the same way as what we did with the resistor? Yes, we can. We are going to multiply the expression for the current, or multiplying the current with the expression for the voltage, which is standing over here. So we are going to multiply the amplitude times the cosine omega times t with the amplitude of the voltage times the cosine of omega times t plus p over 2, and then we get the instantaneous power, which is equal to the amplitude of the voltage, this one, times the amplitude of the current, this one, times the cosine of omega times t plus p over 2, which is written over here, times the cosine of omega times t, which is written over here. Well, by using this Gonio formula, which says that the cosine of alpha times the cosine of beta equals half times the cosine of alpha plus beta plus half time the cosine of the difference of alpha and beta. And in this case, alpha is omega, it's written over here, and the beta is omega times t plus p over 2. So when we write that out, we get the amplitude of the voltage times the amplitude of the current times 0.5, half over here, times the cosine of, well, omega times t plus omega times t plus p over 2, which is 2 times omega times t plus p over 2. And we have plus the cosine of the difference of alpha and beta, so omega times t minus omega times t minus p over 2, which is written over here. So this is the cosine of minus 90 degrees or minus p over 2 radians, which is always equal to 0. So then we get the expression that the instantaneous power at every point in time is equal to the amplitude of the voltage times the amplitude of the current divided by 2 times the cosine of 2 times the omega times t plus p over 2. Here's my double frequency, which we have seen in this graph, and the green graph with respect to the voltage and the current. What we also see is that the amplitude of the voltage times the amplitude of the current divided by 2 can be written as Em divided by the square root of 2 times Im divided by the square root of 2. So this is equal to the RMS voltage times the RMS current. Now let's look to the average power P, the active power, which is the average of this expression. Remember, this is 0 because the cosine of minus 90 degrees is always 0. So we have to take the average of this part, which is the RMS voltage times the RMS currents times the average value of this cosine, and of course the average of a cosine function with t as an argument, so a cosine which keeps on moving in time brings us the value of 0. So my average power is the RMS voltage times the RMS current times 0, which equals 0 watt. And that is what we see in this graph. So summarized, when an inductor, a pure inductor, is connected to an AC voltage or current source, my average power is equal to 0 watt. Okay, that's quite the difference with respect to the resistor. Now let's replace the inductor by a capacitor. And in this situation, we have a AC voltage source, and we connect that capacitor to that AC voltage source. And that AC voltage source is written by this expression. E equals the amplitude of the voltage times, again, the cosine of omega times t. Well, because C is a capacitance, we get this formula, which displays the relationship between the current and the voltage over a capacitor, which says that the current through the capacitor is equal to the capacitor value times the derivative of the voltage. So I equals C times dE dt. So let's do again mathematically. We get I is C times the derivative of that function, C times the amplitude of the voltage times the derivative of a cosine, which is minus the sine, which is written over here, sine times omega times t, but we are taking the derivative to t, so we have to use the chain rule, which says we have to use again the derivative of omega times t in this expression, which brings me omega over here. So this is my expression for the current through that capacitor. Well, my voltage is a cosine, so let's transform this sine into a cosine, and minus the sine of this function is equal to the cosine of the same function shifted by 90 degrees. So we get the current through the capacitor is equals omega times C times the amplitude of the voltage times the cosine of omega times t plus p over 2 radians. So in this situation, because my load is a capacitor, the current leads the voltage by 90 degrees. So I is a current amplitude, which is equal to omega times c times Em times the cosine of omega times t plus pi over 2. Well, we can put this in a graph again to visualize current and voltage, and then we can look to the graphical expression of the power. In this plot, the red curve is my voltage, which is my cosine wave over here, with an amplitude in this example of 1, and the current is the blue line over here, and we see that the peak value of the current is sooner in time um, related to the peak value of the voltage. So we can say again that the current leads the voltage by 90 degrees, what we expected by this expression. We can also calculate the power in time by multiplying again the voltage and the current at every point in time. And then we get the green curve again. And equal to the inductor, we see that the frequency of my power has been doubled, and we also see that the average power is equal to 0 watt. Again, we have as much as positive parts of that sine of cosine with respect to the negative parts. Well, let's do the math and let's see if we can calculate what we have seen in this graph. And then we are multiplying the current and voltage. So my voltage was this cosine expression and my current was this cosine expression. Remember, the current was shifted by 90 degrees, and then we multiply voltage and current, and then we get instantaneous power. And that instantaneous power, P equals the voltage times the current. So this voltage expression multiplied with this current expression, and we get the amplitude of the voltage times the amplitude of the current times the cosine of omega times t plus p over 2 times the cosine of omega times t. And we are going to use the same geometric formulas which we discussed in the example with the inductor. So we get that instantaneous power is the amplitude of the voltage times the amplitude of the current divided by 2 times the cosine of the product of omega times 2 plus p over 2 plus omega times t, which is equal to 2 times omega times t plus p over 2. So here the double frequency is visible again. And we have to take into account the cosine of the difference of alpha and beta, so the difference of omega times t and omega times t plus pi over 2. So omega times t minus omega over t is 0 minus p over 2, which gives us this expression. So again, like with the inductor, this equals the RMS voltage times the RMS current, which is equal to Em over square root of 2 times Im over the square root of 2. When we have to calculate the average power, so the active power P, we have to take the average of this expression and the average of this expression. Remember, this is already 0. So it's equal to Em over the square root of 2. So it's the RMS voltage times Im over the square root of 2, which is equal to the RMS current times the average value of a cosine, which is 0. So my average power is 0 watt, what we also saw with the inductor. So summarized, when you put a pure inductor or a pure capacitor to an AC voltage or AC current source, the average power in that inductor or capacitor is equal to 0 watt. Thank you for watching. See you in video number 3.